Watch a glass shatter on the floor. Now imagine the film running backward. The shards leap up and fuse into a perfect glass. You instantly know that's impossible. But here's the strange part. The laws of physics, at the level of individual particles, don't care which way time runs. Play them backward, and they're just as valid. So why does the world have an arrow of time? Why does the past feel so different from the future? The answer comes down to one word: entropy. Zoom in on two billiard balls colliding. Film it, then play it backward. Both versions obey Newton's laws perfectly. You couldn't tell which one was real. At the microscopic level, almost every fundamental law works the same forward and backward. Down there, time has no built-in direction at all. Yet step back to everyday scale, and direction is everywhere. Heat flows from hot to cold, never the reverse. Smoke spreads out, never gathers. Things wear down, mix, and fall apart. How can a one-way world be built from two-way laws? The bridge between them is a single, deep idea, and it's really about counting. Physicists separate two things: the microstate, the exact position and motion of every single particle, and the macrostate, the big picture description, like temperature or where things roughly are. Entropy measures just one thing: how many microstates look the same from the outside. How many different arrangements give you that same macrostate? A tidy, ordered state, like all the air bunched in one corner, can be built in very few ways. A spread-out, messy state can be built in an astronomical number of ways. Let's actually count with a tiny toy. Just 4 particles in a box split into a left and a right half. Each particle is on one side or the other. How many ways can all 4 end up on the left? Exactly 1. Every particle has to be there. That's a single, special arrangement. How many ways to get 2 on each side? 6 different arrangements, depending on which 2 are on the left. 6 times as many ways as all left. So if the particles just shuffle at random, the even split is 6 times more likely than the all-left state, purely by counting. Higher entropy simply means more ways to happen. Now stretch from 4 particles to the trillions of trillions in a real gas. The even spread isn't 6 times more likely. It's more likely by a factor with more zeros than you could write in a lifetime. That's why a box of gas crammed into 1/2 is a low entropy state. There are only a handful of ways to arrange it. Let it go. Each particle just bounces around, blind and obedient to the laws. But there are vastly more arrangements with the gas spread evenly than bunched up. So, overwhelmingly likely, the gas fills the box. Not because any law forbids it from staying put, but because spread-out states simply outnumber tidy ones by unimaginable margins. That's the second law of thermodynamics. Entropy tends to increase. But notice, it's a statement about probability, not an iron rule. The gas could spontaneously rush back into one corner. It isn't forbidden. It's just so staggeringly unlikely that you'd wait far longer than the age of the universe to ever catch it happening. Boltzmann's critics even proved the gas must, eventually, drift back into that corner all on its own. They were right. But the weight dwarfs the age of the cosmos by a number with more digits than there are atoms in the sky. A shattered glass is the same story. There are countless ways for it to lie in pieces, and practically none that spell out an intact glass. So it breaks and never unbreaks. For a while, physicists wondered if you could cheat the second law. In 1867, James Clerk Maxwell imagined a tiny being, later nicknamed a demon, guarding a gap between 2 halves of a gas. The demon lets fast molecules through one way and slow ones the other. Slowly, one side heats up and the other cools, sorting order out of chaos with no work at all. Entropy seems to fall. For decades, the demon haunted physics. The resolution came only in the 20th century, and it's beautiful. The demon has to remember which molecules to sort. And eventually its memory fills up and must be erased to keep going. Erasing information, it turns out, always releases heat and raises entropy somewhere else. The demon's own mind pays the bill. The second law holds. The man who first tied entropy to counting was Ludwig Boltzmann in the 1870s. He gave us one of the most profound equations in all of science. S equals K log W. Entropy is the logarithm of the number of microstates, a bridge between the invisible world of atoms and the heat we can feel and measure. 8 little symbols carved in stone in Vienna, a key to why heat flows, why time points one way, and why the world unfolds as it does. Boltzmann was mocked for it in his time. Many of his peers didn't even believe atoms were real. He died by his own hand in 1906 before he was fully vindicated. His equation is carved on his tombstone. Now the payoff. The arrow of time, the very difference between past and future, is simply the direction in which entropy increases. We call earlier the direction of lower entropy and later the direction of higher. It's even why we remember the past and not the future. Laying down a memory means first wiping part of the world to a clean, known state, and that wiping always pushes entropy out somewhere else. It's why you can recall this morning, but never tomorrow morning. A memory is a record, and every record is a small island of order, paid for by a little more disorder somewhere else. Time's arrow isn't ticking out of the equations. It emerges from statistics, from there being so many more messy states than tidy ones. But that raises a deeper question. If entropy always climbs, then long ago it must have been lower. Keep going back, and you reach the lowest entropy of all, the very beginning. And that is what we find. The early universe, just after the Big Bang, appears to have been in an extraordinarily low entropy state, remarkably smooth and uniform. That sounds backwards, since smooth usually means high entropy. But once gravity enters the picture, a smooth spread is actually low entropy, because all that matter can still collapse into stars and black holes. It's among the deepest puzzles in all of cosmology. Why did the universe begin in such an improbably ordered state? We still don't fully know. But everything that has ever happened flows from that single, strange fact. Everything since, every star, every snowflake, every thought, has been entropy climbing from that special start. The arrow of time seems rooted in the universe's first moment. And if entropy keeps rising, where does it end? In the far future, everything evens out. No hot, no cold, no gradients left to drive any process. Physicists call it the heat death. Not fire, but a cold, featureless calm, where the ordinary processes that drive change run out, and in a sense, time as we know it loses its meaning. So the next time you watch something fall apart, remember what you're really seeing: the universe counting. Messy states vastly outnumber tidy ones, and that imbalance is time itself. The arrow you feel, from past toward future, was set in motion at the very beginning, by a cosmos that started in exquisite order.